Okay, so here's an example. We have K5 here. So if I wanted to know the best route, I haven't written the weights down yet. If I wanted to know the best route a traveling salesperson could take in this particular complete graph, I'd have to write out 24 different routes, calculate all the routes, then pick the one with the least weight. Okay, well, I don't want to do that. So I'm going to use the nearest neighbor algorithm. I'm going to just abbreviate it. Nearest neighbor algorithm. Okay, now I have to actually label everything. So I'm just making up numbers. And usually in these types of examples, I try to make all the weights different. They can be the same, but I think it's just easier to make them different. Okay, so now that we have K5, there's a lot of stuff going on in here. I have to make sure you can tell what I labeled which way, so I'll make this 34. So that's B to E is 34. Make this, 18. Drop my eraser. How about we make this one a big one? 50. Still have at least one that I haven't labeled yet. This one right here. How about we make that 22? I was looking to see if I have another 22. It doesn't really matter. I think there's only one that I haven't labeled yet. This one right here. How about we make that 38? I think they're all labeled now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, they're all labeled. Okay, so yeah, you would have to write out 24 different routes and then calculate the weight of every tour and then pick the one that has the least weight if you use the brute force algorithm with this particular problem because it's K5. We don't want to do that. We're going to just use the nearest neighbor algorithm. Once again, we're going to say that we're here. So once again, I'm going to go off screen while I drink some Gatorade. Once again, we're going to do a nearest neighbor algorithm starting at A. That's a bad at symbol, but I'm not going to erase it. So, we have to look. A, we have an edge that's weighted 30. We have one 25, 22, 18. This is the shortest edge. In other words, our nearest neighbor is D. Doesn't matter what it looks like on the graph. You're not looking at, oh wait, D looks like it's far away. You're looking at the number. The number is 18. That represents something, whether it's how many miles, kilometers it is. A is from D. It could be how much money it costs to go from A to D. Whatever it stands for, you're picking the smallest number. So A to D is our first move. Okay. Once you get to D, you don't have to look at the A. Remember, we're going to end our tour going back to A. The only options now are to go to either C, B, or E. Well, we have 45, 50, and 40. 40 is the smallest number, so you're going to go from D to E. Okay, once you're at E, the only two vertices we haven't visited yet are B and C. E to B has a weight of 34, E to C has a weight of 38. So you're going to go on the shortest one, so you're going to go to B. Now you have no choice. The only place you have left to visit is C. So you have to go to C, and then you have to come back to A. So it looks like our route is going to be A to D, D to E, E to B, B to C, then C to A. Let's actually calculate what that is. So A to D was 18, D to E was 40, E to B was 34, B to C was 20, and C to A was 22. So we have 40, 80, 134. Let me double check that. Yep, 134. So that might not be the actual quickest or best route, but it's a good route. We definitely know it's not the longest route, okay? I don't think you can ever get the longest route using one of these algorithms, but it might not be the best route. But see how long it took us to do it? It didn't take us hardly any time at all. So it's a good method to use to find maybe not the best route, but at least a good route. Okay, so that's the nearest neighbor algorithm. Let's talk about the repetitive nearest neighbor algorithm, which is basically the same thing. It's exactly what it sounds like. Repetitive nearest neighbor means what you're going to do is you're going to just, I always say pretend, but just because it's a word that makes sense to me. But don't take it as pretend. Take it some other way. What you're going to do is you're going to pretend that maybe you really started here. What you're going to do is you're going to do the nearest neighbor algorithm from starting at A, which we already did. Then you're going to do it from B. Then you're going to do it from C. Then you're going to do it from D. Then you're going to do it from E. They might all give you the same route. But if they don't, what you're going to do is pick the one that had the least weight. So we already did the one from A. So it's basically, let me repeat that again. You should also make sure you look it up in the book and read about it in the book. You're just doing the nearest neighbor algorithm, but you're doing it as if though you were starting at each different vertex. So if you know how to use the nearest neighbor algorithm, then you know how to use the repetitive nearest neighbor algorithm. So I'm going to write that down. Repetitive nearest neighbor algorithm. So we don't have to do it starting at A because we already did it. But now let's pretend we're at B. Our headquarters are now mysteriously moved to B. Hopefully one of these routes that we get is different, okay? So if we're at B, our nearest neighbor is C. I can already tell, I think that this is going to turn out the same. C, our nearest neighbor is A. When we're at A, our nearest neighbor is D. And then we don't have a choice. There's only one left, E, and then we go back to B. If you notice, this route is exactly the same as this route. It just starts someplace different. Look at B, C, A, D, E, B. B, C, A, D, E, B. So I already know what the weight of this would be. It's the same route, so it's 134. Okay, now let's pretend these are all probably going to give the same answer, but they don't always. But in this particular example, it might. Let's say our headquarters are at C. So starting at B. Now we're going to start at C. Our nearest neighbor here is B. When we're at B, our nearest neighbor is A. I think this might be a little bit different. So let's see. C, our nearest neighbor was B. B, our nearest neighbor is A. Now that we're at A, looks like our nearest neighbor is D. Now we only have one choice, is to go to E and back to C. Is this different? I think it's a little bit different. It might, the route's different. The weight might still be 134. Let's check. I didn't have to do the math here because I could tell that it was the same exact route, but this is a little bit different, I think. So we have 20, B to A was 30, A to D, 18, D to E, 40, E to C, 38. All right, so we have 50, 68, 108, 146. So that's not good, okay? So far our best route is still 134. We're looking for one that might be better. But you can see here that it depends on where you start at. Starting at C, it wasn't good. All right, so I'll do starting at D here. As long as you can still see it, you can. So now we're starting at D. Then I might, if 134 is the, if 134 is the best weight, I'm going to pretend like that we found one that was better, and then tell you what you do from there. So starting at D, our nearest neighbor is A. Then at A, our nearest neighbor is C. Then when we're at C, our nearest neighbor is B. Now we only have one choice left, is go to E, then go to D. This might be different too. Yeah, I think it's different. I'm just making sure it's not one of these same ones just written backwards, or actually it might be the same as that. Let's check. So D to A, 18, A to C, 22, C to B, 20, B to E, 34, B to D, 40. So we have 40, 60, 94, yep, see it's 134. It is just the same route in a different order. All right, so we have one last thing to do. Nearest neighbor starting at E. So now we're here. This is our headquarters now. Or we're pretending that it is at least. So when we are at E, our nearest neighbor is A. At A, our nearest neighbor is C. When we're at C, our nearest neighbor is B. Then we have to go to E. Oh wait. Oops, I forgot. We're starting at, forget I said all that. We're starting at E. I started at D for some reason. Should have wrote E here. So when we're at E, our nearest neighbor is A. When we're at A, our nearest neighbor is C. When we're at C, our nearest neighbor is B. Then we have to go to D. then back to E. I think this is going to be the worst one. So we have 25, 22, C to B is 20, D to E, 30, 157. So that's the worst one. Well, instead of changing one of these so that I could show you what would happen, like I wanted to maybe see if we got a better one than this, but let's say to begin with, our headquarters really were here. Okay? So, if our headquarters were really there, and we just wanted to use the nearest neighbor algorithm, we would have used the nearest neighbor algorithm and found out that a good route, or maybe possibly a good route, had a weight of 157 because we used the nearest neighbor algorithm and we came up with 157. We know for a fact now, though, that there's other routes that are better. Well, what you would do is use the repetitive nearest neighbor algorithm, then you would have done all these other ones. Well, what happens is when you find the best route, which is the route with the least weight, so there was 3 of them that wound up with 134. What you're going to do is you're going to pick one of these. So let's just pick this one, since it's the first one that we did. Okay, so this route starts at A and goes to D, then E, B, C, then back to A. Well, we're really at E, though. Our headquarters are at E. So what you do is you just rewrite this route, though, but starting with E. So using the repetitive nearest neighbor algorithm, let's say your headquarters were really at E, you used the repetitive nearest neighbor algorithm and found out that this is the best route. What you would do is just rewrite this route. Now I'm going to erase this down here because we don't want that one because it was really big. You're going to just rewrite this so that it starts with E. So here's E. So you're going to go from E to B, B to C, C to A to D, and then back to E. So, just in case you don't believe me, I'm going to calculate this route here. E to B is 34. B to C is 20. C to A is 22. A to D is 18. And then D to E is 40. So we have 134. So that's how you use the repetitive nearest neighbor algorithm. It's obviously longer than just using the nearest neighbor algorithm. If you have K5 and you use the nearest neighbor algorithm, let's say you're at A and you use the nearest neighbor algorithm from A, you only have to do it once. Well, if you're in K5 and want to use the repetitive nearest neighbor algorithm, you have to do it as if though you're starting at each different one. So you have to do it 5 times and then just pick the best one. If you're in K8, you'd have to do it 8 times. So it's a little bit longer, but you might get a better route. Like I said, for this particular one, if we were really in city E and we just used the nearest neighbor algorithm, we would have gotten a tour that had a weight of 157, which was not good compared to the score we got using the nearest neighbor algorithm starting at city A. So that little extra work that you do might pay off great in the end. So it's worth it to do the repetitive nearest neighbor algorithm. It's basically, if you know how to do the nearest neighbor algorithm, it's the same thing. You're just doing it as if though you were starting at different cities. So that's the nearest neighbor algorithm and the repetitive nearest neighbor algorithm.